from the College by the Lake, Coeur d'Alene, Idaho. Local, regional, national, and international guests discussing the issues and topics affecting the way you live are on Forum, the North Idaho College Public Forum, with your host and moderator, political scientist Tony Stewart.
Welcome to today's program of the Public Forum. We're doing a subject that is of great interest to our viewers, I'm sure, and in recent months and years we've had a lot of problems with earthquakes around the world, and so we are going to pursue that topic. And particularly our question today is, what is the danger of having a major earthquake in the western United States? I have on the program three people today, two panel members and a guest that are highly qualified to address this important question. First of all, I welcome to the program Bill Richards, who's on the faculty at North Idaho College. He's a geologist, and he holds a baccalaureate degree from Stephen F. Austin College in Texas, and he also holds a master's from Kansas State University. Bill, it's very kind of you to come and to take this time to discuss what I know our viewers will believe to be a very, very important subject. And as always, I'm happy to welcome members of the faculty on the panel. And today we have two of my colleagues. First of all is Lloyd Marsh, and next to him is Kurt Nelson, both from the Division or Department of Natural Sciences. Our format will be a little bit different today. I'll start the questioning because of how we've set up the system. And Bill, we thank you for bringing some visuals with you. And we're just going to get right into the question of what are earthquakes. And as you pursue that question in a moment, we'll be putting up on the screen some fault mechanisms as illustrations. But would we start out with a discussion of what are earthquakes?
In general, an earthquake is just the release of energy in the rocks. An earthquake occurs when stored energy is released. And the energy can be placed in the rocks through stresses and pressures building up to the point of the strength of the rock is exceeded and something has to give, and that energy then is dispersed outward into the rocks.
If we can have our staff, they have put up on the screen the first one, and I understand that we can have horizontal or vertical faults. Is that correct?
Correct. This illustration shows a vertical fault movement and shows the energy emanating from the region of movement, which in this picture is beneath the surface. Most earthquakes occur beneath the surface, and then the energy is released outwards in all directions, and some of that energy will reach the surface and cause surface damage.
Now, we also hear about different earthquakes, such as the one in California not too long ago, and sometimes they are very close to the surface, and sometimes they're much deeper. Does that impact in any way the damage?
Well, there's other fault mechanisms, and the next illustration shows a typical subduction zone, what we call a subduction zone, showing with the red dots there faults occurring very shallow, very near the surface, and then deeper focus earthquakes that might extend interior into the continent, and the energy can be released out in all directions from those earthquakes. So you may be quite a ways from the coast and from the subduction zone itself, and the energy is still going to make its way further inland. This would be a good model of the Cascade Range and the especially the Seattle area.
And so, depending on exactly the extent of the intensity and some of the other factors that you're indicating, will determine whether it's very localized or where it's a much more widespread effect.
Correct. The key is the source region and where the energy goes, not necessarily where the fault is or where the fault movement was necessarily. It's where's that energy go, and what kind of damage does it do when it gets there. Here's a summary diagram that shows the middle of the ocean, a tectonic setting there where we have transform and divergent boundaries producing earthquakes. And then again the west coast model where we have subduction beneath the Cascade Mountain Range, for example. And you can see each of those red dots shows an earthquake location. And the energy may extend outward in all directions, and so make its way up to the surface, and depending on what kind of rock it goes through to get to the surface, how strong it'll be when it finally gets to the surface.
Certainly as we look at earthquakes around the planet, we know that some have been much more severe than others. But we also know, and I think Lloyd's going to get into that area too with you, to talk about the measuring of earthquakes, but there are some places, we'll see it later in the program, that have more serious potential, that is, fault lines and so forth. But I know we can pursue that at a later date, but you might want to respond a little bit at this time.
Well, again, it's not so much where the faults themselves are, it's where does the energy go from that earthquake.
Okay.
As the visual showed, the earthquake can be lots of different places, but where does the energy go? That's where the hazard is where is that energy going and what kind of rocks is it going to be going through when it gets there?
Okay. Lloyd Marsh.
I'd like to, while the subject today is going to be the west coast of the U.S., and certainly we'll focus on Idaho and the Northwest, but are earthquakes worldwide? Are they global? I mean, do we have the same problems elsewhere in the world?
Well, of course, there's earthquakes everywhere. People call from California up here and ask, do you guys have earthquakes up there? And of course, we have to say, yes, earthquakes are everywhere. And again, it's where that energy goes that comes out of the earthquake. And the energy could go anywhere. There certainly are tectonic settings that produce more violent earthquake energy. The Pacific Rim is a good example, the Ring of Fire, the tectonic settings of Japan, as we've seen, and the tectonic settings of the Andes Mountains. We don't hear a lot about earthquakes in South America, necessarily, mostly because of the lower density of population. But certainly the west coast of South America has just as many large, violent earthquakes as Japan.
Are there any safe places in the world? I mean, are there places where the energy, the advent of energy released from these earthquakes are less than it is in other locations?
Well, that's a relative question. Safe is a relative term. How safe do you want to be?
Sounds like a professor to
I want to
me.
be 100%. I don't want to ever experience an earthquake.
How long do you want to wait around before there's not an earthquake? I don't think you could say that there's any place on the planet that's not going to ever experience an earthquake. As we're going to see later, there's some areas of the United States that have much milder risk for damage from the earthquakes. And maybe that's the way to approach it, not from the point of view of, is there any earthquake-free areas? What we should look at is, what's the risk of damage from earthquakes in an area?
Great. Kurt?
Bill, a lot of earthquakes you mentioned on the Pacific Rim and the mountain building areas of the South America, the Andes, etc. Can earthquakes occur on flatter ground like the central United States or in Montana, say, away from the coast? Can that happen?
Well, certainly the New Madrid area of Missouri, which we consider Missouri the Midwest to be flat, is a very seismically active area because that's the site of some ancient tectonic boundaries that are still active after millions and millions of years. They may be increasing activity, they may be decreasing in activity, but there's still seismic activity in these old tectonic areas. Even though they're very old, they're still seismically active.
Some people, you know, when they watch movies of earthquakes, etc., and when we've seen some recently on television through the coverage of communications, you'll have one house standing or two houses that haven't seemed to be touched, yet others adjacent to that have just been flattened. Why can that happen, or how does that work, that some are touched and some are not, so close to each other?
Well, the damage from earthquakes tends to come from, and the risk from earthquakes is from falling buildings, from falling material, falling highways. And it depends a lot on the construction material, the construction methods, as well as the substrate underneath the building. If that substrate transmits the energy in a certain way to that building, there's a greater risk for damage. You're sometimes more concerned with the material underneath a building losing its strength, and therefore it loses its ability to support that building. So the building could be as strong as anything, but if the subsurface isn't able to take the strength of that earthquake, you will lose the strength of the support underneath the building, then the building will collapse.
What depths are we talking? You said substrate. How deep are we digging? What a backhoe can reach? Are we hundreds of meters deep, or what kind of material are we looking at on the surface?
The strength of the material we're talking about is from the point of contact with the foundation all the way down to wherever the earthquake energy is coming from.
So it could be quite deep and transmitted up through. The energy could be released through hundreds of yards or even miles, I guess you would say, huh?
Certainly.
Mm-hmm.
The earthquake energy could be traveling through very strong rock, capable of supporting that energy, and then hit a zone immediately beneath a building that's not capable of supporting the strength. And sometimes, in a worst-case scenario, liquefaction occurs, and the material behaves like a liquid, and the liquid couldn't support a very strong building.
Bill, a little bit earlier in the program we talked about that we have a map with us, and our staff will put the map up on the screen in a moment. It's a map of the United States, and so in relation to that, we do have some color coding, I believe, that indicates the intensity. Here we go. Now, if you'd explain.
This is a map published by the U.S. Geological Survey that shows the potential risk for earthquake damage. Not necessarily the potential for an earthquake, but the potential risk for earthquake damage. With the 0, the lightest shade there, being the least risk for damage, and the darkest black there, the region 3s, being the greatest risk for damage. And you can see that the Pacific Northwest, specifically North Idaho, is in the second highest risk category for damage, and we're bounded on the east in the Mission Range of Montana by a very high risk zone, and on the west by the Seattle area and the subduction zone tectonics there.
If I can interject, actually the entire west is, according to those classifications, rather serious, except some parts in Oregon. It looks like the Midwest is much different from the west.
The Midwest is fairly risk-free, except again, if you look in Missouri, southeastern Missouri, the New Madrid, Missouri area, very high-risk area for damage, because there is the risk for seismic activity and because of the material that buildings are put on there. It's very easily liquefied during earthquake.
We just don't want time to pass without getting into this area too. We hear when an earthquake takes place a report of the intensity. I believe there are two different ways of measuring earthquakes, and I know our viewers would like to hear about that, and particularly we hear this was a mild or this was a very highly energized earthquake. Would you take us through how we measure?
There's two basic scales or references or schemes is a better word. The first is the classic Richter magnitude, which measures two things really, the magnitude of the energy released as well as the magnitude of the motion of the earth. And that's the Richter scale. The other scale is the modified Mercalli scale, which measures semi-quantitatively amounts of damage and people's reactions to the earthquake.
In relation to that, the Richter scales that we hear so much about, this was a 3.4, or this was a 7.5. Explain that scale from 1, it goes up usually, what, about 11 or 12?
Well, the Richter scale can actually go from negative numbers
Okay.
up to very high numbers. There's theoretically no real limit, but the Richter scale operates by powers of 10, where each Richter number is a power of 10 of more motion, earth motion. Also, each Richter number is approximately 30 times more energy released than the previous Richter number. So an earthquake with a Richter magnitude of 1 would be 10 times more motion than an earthquake with a Richter magnitude of 0.
And a 2 point.
And a 2 would be 10 times more than a 1, which would be 100 times more than a 0.
Go ahead.
Boy, we're so anxious to get in here. When we talk about energy release, what kind of energy are we talking about? I know we build up stress and we get motion, but is this motion classifiable? Can we classify this motion?
Well, I have an example here to illustrate that, and you could think of the rocks of the earth being exposed to stresses as like a spring. A spring has stored energy in it, and when you disturb that material, you release some energy, the energy is transferred through the material. And that's energy of motion. Kurt's the physicist, he could explain more to us about the actual energy. We could express that energy in ergs and various units of measurement, but the rocks of the earth are like stored energy in a spring. And when that energy releases, the energy is transmitted through the rocks.
Right, and it looks like it does things that energy might be expected to do, and that is to transmit and reflect, maybe come back off a different kind of surface and reflect. We transmit this through waves. I hear words like P waves and S waves. Can you talk a little bit about it?
Well,
difference?
when seismic energy is released, it's released in a wave form, and it's a wave phenomena. And as it travels through the rock, there are P waves, which are push waves, and then there are S waves, which are shear waves that go back and forth like this, and the energy is transmitted by both mechanisms. And the P waves travel faster, S waves travel a little slower, and we can use the P waves and the S waves to help measure the strength of the earthquake, the magnitude, as well as its distance from our seismic location.
Which are the most destructive, the P waves or the S waves? Generally speaking, for buildings and structures that man.
There you're getting into a geophysical question,
Yeah.
and I'm not sure I'm the best one to answer that. The destruction comes from the P waves and the S waves reaching the surface and therefore becoming surface waves. And I don't think we really want to make a distinction between which is more damaging.
Yeah.
But for that to happen, if I can just interject with you, Lord, the pressure builds up to a certain extent to cause that to happen, does it not?
The pressure builds up in the rocks, and that's the
Yes.
stored energy, and then when that energy is released, that's the earthquake. And the energy then transmits through the rocks.
Okay, go ahead, Lord.
Well, just to follow up on that a little bit, I know that we talk about the destructive capabilities of earthquakes and so forth, but we also use this constructively in that we've learned a lot about the interior of the Earth through this energy transfer process. Can you address that just a little bit?
Oh, exactly. To a scientist, to an earth scientist, the seismic energy is a tool. As it goes through the Earth, we can learn about the material it's traveling through. So we've learned a lot about the interior of the Earth by measuring how seismic waves travel through the Earth and come out the other side or don't come out the other side when we expect them to. And to this extent, we've utilized not just natural earthquakes, but artificially generated seismic energy from nuclear testing and from other explosions that we create.
Talking about geophysical exploration techniques, looking for cavities in the earth, etc. Bill, what is it that makes earthquake predictions so difficult? What factors are involved here?
Well, we could spend a whole show on talking about earthquake prediction. There's just as much scientific problem as there is sociological and socioeconomic problems.
Yes.
Somebody has to fund it, and it takes a lot of very expensive, very sensitive equipment and someone to collect all that data. Until we collect enough information, we're not going to be able to reliably predict, and I don't think we'll ever be able to reliably predict earthquakes.
Does this data have to be collected near sources, or can it be collected anywhere in the world? How does that work?
Well, the closer you are to the source area, the more accurate your data and the more sensitive you can be. It turns out if you look at seismic maps, tectonic maps, you tend to see clusters of earthquakes occurring around areas where they have lots of seismometers installed. So that's kind of a problem. You think there's a lot of seismic activity in an area, but then you really look at it, and that's where they have all the seismometers. So of course that's where they're going to measure all the earthquakes.
Something else we want to get on before we get through the program today, another visual. I think that our viewers always like that. You have brought a rock collection with you or something. This is from our local area of an earthquake, I guess a very long time ago. If our staff can put up on the screen what you've brought, then I would have you to explain. I know when you showed me the rock, even when you feel it, you can tell which way the movement of the earth went. And it looks very glassy-like after the activity has taken place. If you could explain that to us.
Well, we're always interested in earthquakes in our area and faults in our area, and I have a sample of what we call slickensides rock. And it's the rock that's actually created along the fault zone, and you'll see how shiny and polished it is here and how striated it is. That polishing occurs from the grinding and the pressure of the movement along the fault. And it's very, very smooth in one direction, but it's very rough in the other direction because that's the opposite direction that the fault moved. So this was taken from an outcrop on Highway 95 just south of Coeur d'Alene, where there's no recorded recent movement along this fault zone, but lots of evidence of past movement, geologically past.
Now that we brought this subject up about the formation of this particular sample of an earthquake here in Idaho, I was reading a publication you gave me from the University of Idaho, and I really commend the University of Idaho. I think it's, Lloyd and I were talking about what an excellent publication on earthquake risk that they made available. And what shocked me when I read it, because I'm not obviously an expert in this area. I think of all the attention of earthquakes in California and in Japan and so forth. But in the last number of years, I believe the 1950s and the 1980s, that the Richter scale registered the two highest levels of earthquakes in Idaho. Is that correct?
Well, that's correct of the recent past.
Yes.
The two of the highest recorded have been in Idaho. One, of course, was the '83 Chalice earthquake down in southern Idaho. But there's been lots of other fairly strong earthquakes in what we would consider recent past as a geologist. For example, in the past 6,000 years in the Mission Range of Montana, there's been earthquakes that have been estimated to have been 8 on the Richter scale. And to a geologist, that's a very recent earthquake, and that's a fairly strong earthquake, too. If that were to happen today, of course, the population centers in central Montana would be greatly affected.
Mm-hmm. Lloyd Marsh.
Mm. Well, and that brings us back to more of the local area, and it looked like on that original map that we had that it's the Wyoming, Nevada, Idaho, Montana areas that are particularly prone to earthquake. And then I noticed there was a little spot up there in northwest Washington. Is that unique? That little glitch up there on the Canadian border?
That part of northwestern Washington is the subduction zone area, which extends up into British Columbia, and that's the potential risk there, is because you have those subducting slabs, and that's what's creating the Cascade Range themselves.
Right. Now, along with earthquakes, we also experience volcanic activity, don't we? And they are related, I assume.
That's a good point. Volcanic activity can be associated with subduction tectonics, and that's what can create earthquakes as well. So you sometimes get the combination of both. You get volcanic mountains as well as the earthquakes. Best example would be Japan, again, because they're an island made of volcanoes. Just like the Andes are a chain of mountains along the west coast of South America. They're volcanic mountains, and they're associated with lots of seismic activity.
So Mount St. Helens in 1980 was sort of this kind of activity, this volcanic activity along the Pacific Rim. And did we experience any seismic activity as a result of the Mount St. Helens?
Well, Mount St. Helens seismic activity was related with the magma moving beneath the volcano, and so that creates smaller earthquakes. They're both part of larger scale processes, the whole tectonic mechanisms that shape the outer part of the crust.
Right. So in addition to this stress that we create in building up this potential energy in the spring, we also have magma activity, which can create
the magma
earthquake.
The magma moving itself creates stresses, puts stress on the rocks, which can cause earthquakes.
Yeah.
Kurt?
If our viewers want more information on earthquakes or regional indications of earthquakes or past history of geological formations, where can they obtain such resources, or libraries or agencies, or et cetera? What ones would you recommend?
The best resource would be the State Geological Survey, the Idaho Geological Survey, which is housed on the campus of the University of Idaho, as well as Disaster Services in Boise. They combined put out very good publications on seismic risk, as well as what to do in the event of an earthquake and how to earthquake proof your house, or how to prevent major damage.
Can I just interject too, Kurt, while we're on this?
Yes.
In other states that are viewing this program, I would assume universities in those states have the same kind of data that at the major universities.
The best resource would still be probably your State Geological Survey, which is usually in conjunction with the major university in the state.
Mm-hmm. Another thing that this brings to mind,
Sure.
while you're asking, we hear about what to do if you're at home, especially when tornadoes hit and hurricanes. There's been a lot of advice. Also, I know there is advice too for earthquakes. If you have time to act and so forth, if you're in a building, should you leave the building? What's the most safe action you can take?
That's a really good question. A lot of times in an earthquake, you're not going to have time to really react. So thinking ahead is a good plan. in an earthquake, if you're indoors, you should stay indoors and use the old rule of duck and cover. Find something heavy to get underneath, get inside of a doorway, stay away from windows. If you're outdoors, your major risk is from falling objects, particularly buildings. So get away from walls, get away from buildings, and get away from power lines and power poles that can fall. That's where your major risk is.
Lloyd?
Does the state of Idaho consider earthquake resistance in a universal building codes? In other words, are there statutes that say you have to meet certain codes? Are you familiar with that?
I'm not one to speak to them specifically, but I do know there are uniform building codes which state seismic risk for various zones, and the county and the state will require those codes be met in certain buildings, yes.
Kurt?
Yeah, there's some codification on buildings, and it depends on agencies and the type of buildings. And I think as a local owner of a home or somebody that's in the Northwest and they're just living, is there any danger to earthquakes that you have to worry about, or can we just feel at ease and go on with our life?
Well, in this part of the country, in North Idaho and western Montana and northeastern Washington State and British Columbia, I think the major concern for a private homeowner would be things that are easily prevented, like breaking of gas pipelines. If you have a gas water heater, you should use flexible gas lines on your gas water heater. So if the gas water heater tips over, the line won't break. Strap your water heater to the wall so it won't tip over in the event of seismic activity. Protecting against those kinds of accidents is easily done.
We're just almost out of time. We have less than a minute. But I want to get in one final question, and that has to do with, it's a rather theoretical one to say the least. Is there a potential for an earthquake that is so massive, its energy is so worldwide, that there could be an incredible catastrophe that would not be as localized as past earthquakes?
That's a good question. As a geologist, I'll never say never. It could happen, and it might happen. It won't happen in my lifetime, I don't think, but there's no reason to say that it couldn't happen.
On that note, we have to bring the program to conclusion. We gave our viewers some other things to think about, I think, with that final question. Again, Bill Richards and the panel, thank you for this most informative program.
My pleasure.
Ladies and gentlemen, as you know, we've been discussing earthquakes, and we hope this has been helpful to you, and we'd like to invite you to be with us again next week, when at that time we will discuss what we believe is another very important issue in your life, and we always appreciate your viewing this program, and we invite you to contact us at any time. Until next week, please have a good week. I am Tony Stewart.
The North Idaho College Public Forum was videotaped live from the studios of Instructional Technology on the campus of North Idaho College for viewing at this more appropriate time. We invite you to join us again next week for another all-new edition of the North Idaho College Public Forum on this public television station.